I'll be giving you a very high-level survey of the science areas, the applications, and the methods that have been developed and are deployed and now running science on the first generation of exascale computers for science and engineering in the US. What I hope maybe you can take from this is that if you have or envision an exascale problem, you should be optimistic that your methods and approaches can be targeted to these systems if in fact they haven't already been. So by the first exascale systems, I mean these three here exactly. The first to come online was the Frontier system at Oak Ridge National Lab at the Oak Ridge Leadership Computing Facility. Next up after that was our own Aurora system at Argonne at the Leadership Computing Facility there. And these computers serve the general scientific computing community through an annual open call for proposals to a program called Insight. It's highly competitive, but it awards very large blocks of computer time for free, if you will, to deserving projects that have a need for capability computing. And what that means, if you boil it down, is you need to demonstrate that you need at least 20% of one of these entire systems to run your calculation. And it's not practical to do so on other systems. The third system, and most recent, is El Capitan, which you've heard about in other talks here, at Lawrence Livermore National Lab. So this system is destined to go behind the fence and be deployed for nuclear stockpile stewardship calculations funded by NNSA. One thing I'd like to point out is all of these systems are GPU accelerated. In the most recent version of the top 500 list from last November, El Capitan came in for the first time at #1 on the 64-bit HPL LinPack benchmark at over 1.7 exaflops. This pushed Frontier down to the #2 position at 1.35 exaflops, and Aurora sits at #3, where we measured just over 1 exaflops on just over 9,200 nodes of the system. I'd be remiss if I didn't call out that Aurora sits at #1 in this HPL mixed precision benchmark, which is meant to be a rough proxy for machine learning operations, where we've measured 11.6 exaflops. I won't say much more about El Capitan after this. I'll focus mostly on the other two systems, and most especially on Aurora, since that's the one that I know the most. These diagrams show the bottom level of each of these systems. The Frontier node on the right is a single AMD CPU and 4 AMD GPUs. These are the MI250X GPUs, particularly with 128 gigabytes of high bandwidth memory. These are all connected all-to-all with AMD's Infinity Link connection fabric, and as is the rest of the node, going out to 4 of these HPE Cray Cassini NICs. The Aurora node on the left is 2 Intel CPUs, specifically the Sapphire Rapids, each with 64 gigabytes of on-package high bandwidth memory. Those also have 512 gigs of DRAM, as does the CPU on Frontier. This node has 6 of the Intel Data Center GPU Max Series GPUs, which is the last time I will ever say that, and I will refer to these as PVC or Ponte Vecchio GPUs going forward. Those are connected all-to-all with Intel's Xe Link, and the rest of the node is connected via PCIe, including through these 2 switches out to 8 NICs of this exact same kind as on the Frontier system. So one ramification of this for scaling out very large is that the Aurora system has a third more bandwidth per GPU to the global network. Just to give you a sense of the full systems, most of this is just for reference. Aurora is made up of 10,624 of those nodes. The only thing I'll call out here is the storage system, which we are still developing to some extent, but is, rather than a file system, it's an object store. And because it is not bound by the limitations of block-based file access, can achieve extremely high performance. The Frontier system has 9,408 of its nodes, and the rest of the details for those who care. It's worth making note of what the precursor systems to these were, specifically at the LCFs. These were also both GPU-accelerated systems. And at ALCF, we have Polaris, which the node looks like this. It's an AMD processor and 4 NVIDIA A100 GPUs with 40 gigabytes of HBM. Again, with an all-to-all fabric connection, everything out to 2 of the Cassini NICs. The system at Oak Ridge was Summit, and it's a much larger system, but architecture-wise, it's similar. Each node has 2 Power 9 GPUs connected to 6 previous generation NVIDIA, or CPUs rather, connected to 6 previous generation NVIDIA V100 GPUs with 16 gigs of RAM. So you will note that both of these systems are NVIDIA GPU accelerators, in contrast with the Exascale systems, all of which are not NVIDIA accelerated systems, but AMD and Intel. And I'll come back to that a little later. So there are a number of programs for developing the applications I'll mention for these systems. Probably foremost, which all of you, or many of you are familiar with, is the Exascale Computing Project from the Department of Energy. This is a DOE-wide effort managed by the Oscar office, a big project. It touched over 2,800 people, and in a very unusual move for Oscar, it actually funded application development. And it did that through 21 of these application or AD projects. So of those, 15 of them came to us at Argonne and worked very closely with us specifically to target the Aurora system, in addition to targeting the other Exascale systems. All of these projects to zeroth order are interested in being able to run across all of these systems. The other program is the one that the facilities themselves run. So every time we stand up a new system, we run something called the Early Science Program at Argonne. And this time around, I managed this with Venkat Vishwanath, and we competitively chose 19 projects from institutions all over the place, scientific areas all over the place, and we funded that, supported that in several ways, including a set of 2-year postdocs to work with the projects and partial funding for people on the computational science team where I sit and the data science team to work with them to get ready for the system. We were very lucky to have the Intel Argonne Center of Excellence over the last 5 years, which kept us on the order of 5 full-time Intel staff working exclusively with us and these ECP and ESP projects, and that made a tremendous difference in progress. Frontier has a similar readiness program that they run called CAR, and for the Frontier system, they had 8 projects, and then they engaged in a sort of add-on partnership with some of these ECP projects. So all that development, all that readiness programs, that's all in the past now. The Frontier and Aurora systems are in production. Aurora as of January 27th of this year, so fairly recently. But that means that we know now exactly what all of the first-year science projects are on the Aurora system. And those come from 3 different origins. One is the early science program that I mentioned before. And across those projects, we've allocated almost 20 million node hours to run science campaigns that they had proposed originally. The second is the Open Insight program I mentioned at the beginning. We have 30 projects running science on Aurora now, and 4 with small allocations that are doing code porting and tuning with the idea to run science in subsequent years. Insight supports multi-year projects. The third is ALCC, This is a program managed by the Department of Energy, and Oscar, in collaboration with the other Office of Science offices, Fusion Energy and High Energy Physics, selects projects through their own process. We have 13 of those this year, with 5 million node hours allocated for the first half of the year. The pie chart up in the top is the steady state breakdown of how we allocate cycles on the Leadership Computing Facility. 60% of them go to this Open Insight program, 30% to the DOE ALCC program, but 10% is director's discretionary. And we provide these allocations, modest in size, on a rolling basis throughout the year. It's a very low bar to request and get one of these allocations. And I would strongly encourage any of you who would like to try out this system or the companion system at OLCF to try one of these discretionary allocations to do so. And I, David Martin, anyone else at LCF is happy to work with you on how to do that and you know what a good approach to take might be. All right, of all of those first-year projects, the one that I know the most about are the early science projects from several years of deep immersion in those. And one of the things that we did was to have a targeted call for proposals, a special one calling for projects with significant components of data-intensive computing and AI or machine learning. And the reasoning for that is because we need to build support for our relatively recently updated mission at the LCF to support the so-called 3 pillars of simulation and data and learning as peers, while also bootstrapping all of this up to Exascale. I won't say much about the simulation pillar. I'll just call out the figure there, which is molecular dynamics simulation with a force field, neural network-based force field derived by machine learning. It is of activation of a skyrmion superlattice, activating the spins with light. This project is a collaboration with an experimental group at USC that fabricates layered nanomaterials and zaps them with layers to activate the functionality. In the data pillar, we, partly by choice and partly by luck, have a representation of a wide spectrum of different kinds of data. So this includes probe data, the traditional 0D, also 1D, and now some 2D data from tokamak experiments. It includes observational data from a collection of multispectral deep sky survey telescopes, Earth and space-based. It also includes looking at data and analyzing data and using data from running exascale simulations. For example, lattice-Boltzmann simulation of blood flow through the entire human circulatory system that is used to transport cancer cells and study the process of metastasis. A lot of that analysis happens in situ, including time-dependent visualization of flows and behaviors of the objects transported. Another kind of data is represented in the figure in the middle. So this is a computer reconstruction of neurons and synapses derived from brain tissue data from a high-throughput electron microscopy system, which takes a cube of brain tissue and slices it up and pipelines it through an electron microscope to produce images. In the learning space, we also were lucky to have represented a variety of different flavors of neural networks, different topologies, approaches to training and hyperparameter tuning. The figure shows, illustrates a transformer model, which takes in molecular data in this SMILES format and is used as part of a larger AI workflow, including natural language processing, that is doing cancer drug design. there's a generative model, what's called a flow-based generative model for lattice QCD. This model is trained by a running exascale lattice quantum chromodynamics calculation and is used in inference to accelerate another lattice QCD calculation, the kind of simulation acceleration that was talked about some in the past and other talks at this conference. The basic idea behind it is that you can more effectively, you can do more effective Monte Carlo sampling, which is at the heart of lattice QCD. Going back to the brain tissue project, the data there is used on Aurora to train a flood fill network model. Which, that architecture comes out of the Google Brain project. It is, the training is not insubstantial, it's on a subset of the data, but for this project, the bulk of the calculation is actually a massive inference pipeline. So you have petabytes and petabytes of this data coming through, you run inference on it and generate the connectome for what in this field is considered a very large section of brain tissue. If you consider the tokamak data, it's almost the other end of the spectrum. The training is very intensive, so that is viewed as an exascale problem. And the model itself, though, is lightweight, and it is meant to be embedded in the control system of a tokamak. There's an attempt to do that, which got delayed a bit because of the cycle of the experimental shots at D3D, but it's there, there's a GPU to run it, and the model is trained to predict plasma disruptions in the tokamak in real time and enough in advance to be able to actuate mitigating controls in the experiment. Okay, so to kind of wind towards the end, here I've shown a categorization of the numerical methods and computational science methods that are encompassed by these first-year projects. It's a lot. Even within molecular dynamics, we have reactive, quantum, classical. I didn't show it, but there are ensemble methods as well. In quantum chemistry, there's a rich variety of electronic structure methods that have been implemented, everything from DFT to high-order perturbation theory, GW-BSE approaches, and high-accuracy quantum Monte Carlo. In what I've labeled as particle methods, we have Monte Carlo neutron transport, plasma particle and cell simulation that I've worked on, P3M gravity simulation for cosmological simulation. In CFD, it's really a pretty full zoo of methodologies. Finite element, finite volume, SPH, lattice Boltzmann, structured meshes, unstructured meshes, AMR. And in AI, I've already talked a bit to this, a variety of model architectures, approaches, Gaussian process approaches. There's a large language model called Aurora GPT, which is being developed as part of a project to develop a foundation model for science. I didn't say much about the ECP applications. Those are not those projects do not literally run on the system, although there's a large amount of overlap, as you might expect, of the applications and some of the project teams. And if we include those 15 extra projects, it brings in a few more methods not captured by the first-year projects. Here just gives a survey of the science domains represented. I've tried to be a little more specific than just physics or chemistry. I'll let you peruse this later, but grouping things roughly at the top left is engineering CFD calculations, fusion energy, what I classify as computer science, astrophysics, material science, high energy physics, chemistry, biophysics, biology, earth science. Here, if we consider those 15 extra ECP applications, it's mostly the same set of areas. One exception to that is seismic wave propagation. The SW4 application was ported to this system. That's for forward wave propagation for earthquake hazard analysis. So before showing a breakdown of how people programmed these different applications, I'll just say a few words about how you do program the system. I'll start with the AI side of things, and for the most part, the data-intensive side of things. This community, I think, is relatively speaking in better shape than the simulation community with respect to consensus on high-level approaches to programming. By and large, there's a Python ecosystem that everyone uses. There are high-level frameworks like TensorFlow and PyTorch that everyone uses. And there's an expectation, so far fulfilled, that the hardware vendors will implement efficient implementations under these high-level programming layers for their hardware, specifically for their GPUs, for offloading to them. And the reason for that is not because we have these computational science applications that want to do it. It's because of the real market for the GPUs, which drives this. There's an expectation that my model doesn't run on your system, make it run on your system. So on the simulation side, things are, I would say, less tidy. There's a lot on this slide, and I would say every single bullet on it, except for the first two, should have an asterisk and a 2,000-word footnote with caveats. But the first two really address the CPU and internode communication side, which I would argue is a solved problem. The use of OpenMP threading and SIMD directives to get efficient CPU execution is widely adopted. Likewise, at least intranode and to a pretty large extent intranode communication via MPI is something that you can expect to work well to a certain point. On the GPU side, it's less pretty. One approach that one may take is the more recent OpenMP standard use of OpenMP target for offloading calculations to the GPUs. And many of these projects did take that approach. If you don't do that, then you need some other means for GPU kernel programming. And going back to our earlier point that all the systems before this at the LCFs were NVIDIA-based, what that means is that we had a bunch of projects that had implemented their applications in CUDA. And there's long history considerably before that of the scientific programming community doing that as well with CUDA. That, of course, is what NVIDIA wants you to use. And we do not have an NVIDIA system. What AMD will tell you to use is HIP, which is as close as you can get to legally to a clone of CUDA with a string replace of CUDA for HIP. But it's not a language extension. That's one difference. It's C++. And they would have you use their tool Hipify to ingest your CUDA code, create HIP, and then throw away the CUDA, and claim that CUDA runs on other systems. There is, in fact, an implementation on NVIDIA. There's a project based largely out of Argonne called ChipStar, which has a nascent implementation of CUDA for the Intel GPUs. But what Intel would have you do, because they are strong advocates of the SYCL kernel programming model, and it's now an intrinsic part of their one API compiler stream, is to use their Cyclomatic tool, which ingests CUDA and outputs, close to ready to run SYCL. You fix that up, throw away the CUDA, and then run SYCL everywhere. We have projects that have been experimenting with that, running SYCL on all three of these GPU architectures, often with good results, but I wouldn't say that's widespread. OpenCL is there as well, but to 0th order, nobody uses it. Another approach one may take is using a higher level portability layer. There's been some discussion of that in other talks here as well. This is something I advocate. These are things like Cocos and Raja, which offer abstraction layers where you write to a single API, and the implementation of that is written in the best way for each GPU. So there's a CUDA implementation, a SYCL implementation, and a HIP implementation. One may also define one's own portability layer, and some of these projects did this through the use of libraries or macros or other means. And that's mostly discussing if you have a GPU implementation, how might you run it on these systems? If you don't, well, I'm sorry for you. This is the hard part. You have to almost certainly refactor some significant kernels from your application in order to not do things that don't play well with the GPU. Your beautiful code that pulls in a single cache line of memory and goes through it in that order in address space to get nice vectorized CPU execution may well not run very well on a GPU. So you may need to do things like modify or invert your data structures to get appropriate latency hiding and optimal memory accesses on the GPUs. You also need to beware of branchiness and other un-GPU friendly things. A point to make about this is that you can do that work, which is hard work, using any GPU kernel programming approach, and then transliterate or make modest changes to move to a different kernel programming approach. But if you're going to do that, why not consider a high-level approach that abstracts things away? One advantage to that is that some of these systems like Cocos and Raja provide you more or less single source that also executes optimally on CPUs as well as GPUs. So looking across the first-year projects, these are the choices that were made. I've sort of grossly simplified the AI side of things by putting everything that looks like a Python framework into one piece of the pie, AI frameworks. So the rest of it is a breakdown of the compiled language components of these workflows. It's worth noting that many of these are multi-component workflows, and so two different components in one project may use a different programming model. And some projects actually have two different applications associated with them that are run independently for parts of the calculation. So if you are counting things up, that's an important caveat. We have strong representation with the OpenMP target approach. All but one of the Fortran projects took that approach, but two of the fairly hardcore C++ projects took that approach as well. And I've been convinced by people that are better performance engineers than I that you can do almost anything with OpenMP target that you can do with other kernel programming approaches. On the AI framework side, as I said, there's been a strong requirement on Intel for Aurora to implement efficient implementations of these AI functionalities. Of course, some of the hard parts are the scale up to Exascale. And if you look at some of the scaling approaches that have been done and communications approaches that have been done in other systems, they don't necessarily easily transliterate onto the Aurora system. So a lot of work is ongoing to address that to successfully reach appropriate scaling efficiency at Exascale. The SYCL applications here include some that have written their own portability layers. And Cocos is quite popular among the first-year set of applications. And part of the reason for that, I think, is we have a number of DOE applications represented, and it's a DOE-originated programming layer, although it's now being turned into a sort of open foundation-based product. The CUDA, QUDA, and GRID layers here are something that the US Lattice QCD community wrote as portability layers. So one may now implement the higher level Charm, Milk, other Lattice QCD calculation applications or new applications on top of these. We have a lot of Lattice QCD representation at this system, so I thought it was worth calling that out. libseed and Oka are by and large for CFD engineering applications. Oka in particular is the portability layer for the NEC-RS spectral element CFD application that originated at Argonne, and we have a lot of projects using that. If we include those 15 ECP projects into the mix, for the most part, it's just a few shifts of numbers. The one new thing is the appearance of one project using the Raja portability layer that comes out of Livermore, and a few more projects that are using HIP to run on the Aurora system. I'm not sure how I'm doing for time. I have a little bit on performance. Okay. I can show a little on performance or take questions. I'll show a little on performance. What did we expect for performance? What ECP expected from 11 of those 21 applications projects was to demonstrate a 50 times improvement in a figure of merit performance benchmark defined by the project on the Exascale system versus a baseline system from 2017, which was the era of 20 petaflops-ish systems. Because of the timing of the ending of ECP and the delay in the delivery of the Aurora system, not many of these projects had an opportunity to try to run this on Aurora. I have some charts on the same data from Frontier. I don't have it with me in this deck, but these three projects, Exalt running a LAMPS molecular dynamics simulation was able to measure almost 90x performance improvement using only a tenth of the nodes on the Aurora system. ExaSMR ran an OpenMC Monte Carlo neutronics calculation on half that many nodes and achieved nearly an 85x improvement versus that baseline. Exascale is a coupled gravity hydrodynamics cosmology simulation that ran on less than half the nodes and achieved over a 275x performance improvement. What we did for the early science program, since part of the reasoning for that is to get teams and projects and codes ready to submit proposals and be our first production users on the system, we evaluated their performance the same way we do when reviewing proposals to the Insight program. And it's all about scalability. So the gist of it is demonstration on this Exascale platform that you can scale out efficiently to at least 20% of the system, so the order of 2K nodes in the Aurora system. Another thing we did, working across all of the ESP and ECP applications targeting the Aurora system, was look at kind of the fine-grained performance. So we asked each of these projects to define a single GPU performance figure of merit. And every quarter for about 3 years, we surveyed all of these projects and asked them questions like, have you ported to a programming model that's supported on Aurora? How close are you to being able to run the actual science case? And also, we asked them to measure these performance metrics. So we kept track of those over time. And our expectation was, based on the hardware alone, that the PVC GPU should be expected to give comparable single GPU performance to the MI250X. And likewise, it should be giving something better, at least, than comparable performance from the A100 NVIDIA GPU, which on our prior generation system. So this shows across a bunch of those applications that this is a snapshot as of a year ago where we were convinced that we had met that expectation of performance. So thank you.
Thank you, Tim. We now have the hard task that lunch is next, so we'll take one question, and then maybe I'll encourage people to come up if they have more questions. But and of course, it's way at the back, so let me get back there.
Thanks for the presentation. This is really interesting stuff. So I'm wondering, in the performance, when you're seeing these big speed-ups, is this just sort of bringing applications to these newer GPUs in sort of the way that they had existed in prior generations, or are you looking at things like reduced precision? And if so, how are you seeing results in terms of accuracy and issues around that?
Yeah. So this performance is the former of those two. So these are applications that have already been developed one way or another for GPUs, and just looking at the differences in the hardware. So we should expect that the hardware has more execution units, et cetera, than the previous one. So you should expect more flops, basically. And on the other area you asked about, which is use of mixed precision and other more holistic changes, one of the things that the ECP allowed was, completely rewriting the code, changing the algorithm, changing the data structures. Anything goes. The one thing that it didn't really capture was replacement of HPC simulation algorithm components with AMR with AI models. The ECP kind of predated the exponential part of the AI revolution, so it had limited representation in that area. That's the kind of thing that we're looking at now. We're trying to spin up a program at Argonne toward the next generation system where we know we're not going to get more 64-bit flops. We want to consider all possible avenues, including surrogate models, reduced precision, and other means to get more performance.